Welcome back. Today, we will create a convolutional neural network from scratch. This is something I looked for myself for quite a while, without ever finding a satisfying answer. So, I want to bring my contribution to this subject and actually show you the math and the code of convolutional layers. This video is going to rely on what has been done before. So, if you haven't seen the first video yet, I would strongly advise you to go ahead and watch it. Without further ado, here is the plan for today. We'll start with a quick introduction about convolution. Then, we'll go through the mathematics and the code of the convolutional layer. We could stop here, but I want to show you an actual use case of that layer, and for that, I decided to solve the well-known MNIST dataset. We'll talk about this in detail later, but for now, know that in order to achieve that goal, we will need to implement a few more things, namely, the Reshape Layer, the Binary Cross Entropy Loss, the Sigmoid Activation, and then we'll solve MNIST. Before we go any further, know that the code that we'll be using throughout the video can be found on my GitHub repository, and the link is in the description. I guess we are ready to start, so let's tackle the first point, that is, the convolution. You are given an input matrix, arbitrarily big, and a smaller one that we call the kernel, or filter. The convolution between the input and the kernel will produce another matrix. The values contained inside the output matrix are obtained by sliding the kernel on top of the input, and by performing a multiplication of adjacent values, then summing them up. Notice how the size of the output can be easily computed as the size of the input minus the size of the kernel plus 1. You've probably seen all this before, but the truth is, this isn't convolution. This operation is actually called cross correlation, and this is important because later we are going to use Python functions, and one is called convolve and the other correlate, so we need to understand the difference. The real convolution is that same operation I showed you, except that you have to rotate the kernel by 180 degrees. In other words, the convolution between I and k is the cross correlation between I and the rotated version of k. As it turns out, there is a symbol for each of these operations. The star denotes cross correlation, whereas the asterisk denotes convolution. Throughout the video, let's just think of the cross correlation as the main operator. You might also hear me say correlation instead of cross correlation, just know that I mean the same thing. Alright, I need to show you one last thing before we go on. There are multiple ways in which you can perform the cross correlation, and hence the convolution. What I showed you is called valid cross correlation. This means that you start computing the product by placing the kernel entirely on top of the input, and stop sliding the kernel when it hits the border of the input. But there is another way you can perform this operation, called the full cross correlation. We will write the full cross correlation as a star with the label full beneath it. In this mode, we start computing the product as soon as there is an intersection between the kernel and the input. Notice how the size of the output is bigger than previously. Now that we cleared this out, let's get to the core content of the video, that is, the convolutional layer from scratch. The convolutional layer takes in a three-dimensional block of data as input. In that case, the depth of the input is 3. The layer has trainable parameters, amongst them the kernels. Each kernel is also a three-dimensional block that extends the full depth of the input. The layer may have multiple kernels, all of which must extend the full depth of the input. To each kernel, we associate a bias matrix that will have the same shape as the output. Finally, the layer will produce a three-dimensional block of data as its output. The depth of the output is the same as the number of kernels that we have. Let me show you how the output is actually produced. Take each matrix in the first kernel and compute the cross-correlation with the input data. Now sum the three results and add up the first bias. This will produce the first output. Likewise, the second output is computed by taking the sum of the cross-correlations between the input image and the second kernel, plus the second bias. Now, we don't really need to bother with that much granularity, so we will give each matrix a simple notation. We can now explicit the formula for each output matrix. The first output is nothing but the first bias plus the sum of the cross-correlations between the input and the first kernel. Likewise, the second output is equal to the second bias plus the sum of the cross-correlations between the input and the second kernel. Of course, the layer doesn't have to be limited to only two kernels. We can have as many as we want. Let's call that number d as the depth of the layer and therefore the depth of the output. We can also generalize the shape of the input. Currently we have an input of depth 3. Let's call that number n. Now, this, my friends, is the forward propagation of the convolutional layer. We could write that more concisely using a sum. Alright, we can already create the convolutional layer and start implementing the forward method, just like we did in the previous video. However, before we do that, I would like to show you something fascinating I realized while I was doing these animations. It's nothing that you need for the rest of the video, so you can skip that part if you want to using the chapter's timecodes below. Here it goes. This is the forward propagation equation that we found. If we expand that, we have a system of d equations. Now, whenever you see something like this, it is super tempting to just factorize this into a single equation using matrix multiplication. Except that we can't really do this here. You see, these variables are not scalars, they're matrices. And the stars, as you know, are not multiplications, they represent the cross-correlation. So that doesn't really work. Still, let's pretend for a second that we have an operator that does what we want. Let's factorize these equations. This operator here, as far as I know, doesn't exist. I just made it up. It's basically a dot product, but instead of computing a multiplication between scalars, then summing them up, we perform a cross-correlation between matrices, and then we sum them up. Once we accept that notation, we can write the forward propagation of the convolutional layer in a single equation. Does that equation look familiar to you? It is the exact same equation that we had for the dense layer, except that instead of having matrices of scalars, we have matrices of matrices, and instead of a regular dot product, we have that cross-correlated dot product. It's not just that this equation looks like the equation of the dense layer. It actually is the equation of the dense layer. Think about it for a second. If each of these matrices were one-dimensional, meaning that each matrix contains a single element, then the cross-correlation between two matrices containing one element is equal to a one-dimensional matrix containing the product of both of these elements. And therefore, this new operator ends up being a simple and regular dot product. So, what I'm trying to say is that the convolutional layer is nothing but a generalization of the dense layer, or rather, the dense layer is a particular case of the convolutional layer. Isn't it crazy? Anyways, let's go back to what we were doing, that is, implementing the forward method. The convolutional layer inherits from the base layer class that we have created. The constructor takes in three parameters: the input shape, which is a tuple containing the depth, the height, and the width of the input; the kernel size, which is a number representing the size of each matrix inside each kernel; and the depth, which is also a number representing how many kernels do we want, and therefore the depth of the output. We start by unpacking the input shape. Then, we compute the output shape. You see that it has 3 dimensions. The first one is the depth, that is, the number of kernels. The last 2 are the height and the width of each output matrix, and are computed according to the formula that we saw at the beginning. That is, the size of the input minus the size of the kernel plus 1. The following line computes the shape of the kernels. This one is 4-dimensional, since we have multiple kernels, and that each kernel is a 3-dimensional block. Looking at these 4 dimensions, the first one is the number of kernels, or the depth. The second one is the depth of each kernel, which is the depth of the input. And the last 2 are the size of the matrices contained inside each kernel. Finally, we initialize the kernels and biases randomly. Note that we don't have to create a variable containing the shape of the biases, since they have the shape of the output. The forward method takes in the input and computes the above formula. We start by copying the current biases, since each output is equal to the bias plus something else. Then we create 2 nested for loops. The first one goes through the output depth, the second one through the input depth, and keeps adding values to the output. You can see that we have used the SciPy library to compute the cross correlation. Be mindful when using that function, it is not commutative, meaning that the order of the parameters matters. Notice also how we specified the mode of the correlation as a loss parameter. And that's it for the forward propagation. Pretty short, wasn't it? Okay, now comes the hard part. In order to update the kernels and biases, we need to compute their gradients. If you remember from the last video, this is how we proceed. We are given the derivative of E, the error of the neural network, and we need to compute 2 things. On one hand, the derivative of E with respect to the trainable parameters of the layer, namely, the kernels and biases. On the other hand, we need to compute the derivative of E with respect to the input of the layer, so that the previous layer can take it as the derivative of E with respect to its own output and perform the same operations. So, we will start with the derivative of E with respect to K. This is the equation of the forward propagation. If we expand the sum, we get this. Now, dealing with all these terms can be quite daunting. Therefore, I'd like to crop that equation just for a moment and work out the calculations on a simplified version. Y equals B plus X correlated with K. If we actually write down what each output variable is equal to, we get this. That set of equations is totally equivalent to the representation using matrices, so we'll keep this. Remember, the goal is, given the derivative of E with respect to the output, try to compute the derivative of E with respect to the kernel. As an example, we can start with the derivative of E with respect to K11. Using the chain rule, we get this, and the terms we are looking for are the derivatives of y with respect to k11. Looking at the forward propagation equations, you see that k11 appears inside every equation. The derivatives we are looking for are simply the factors multiplying k11 in each equation. If we do this for all the other elements of the kernel, we get this. Take a moment to make sure this is correct and try to figure out a way to compute the 4 derivatives in a single formula. The first thing you can say is that the result is obviously an operation between the input matrix and the matrix containing the derivatives of E with respect to the output. Can you see what is happening here? This is nothing but the cross correlation between the input matrix and the output gradient. So, we just figured out that if y equals b plus x correlated with k, then we know how to compute the kernel gradient. That's all good, except that it isn't the forward propagation equation that we have, but rather a simplified version. The actual equation is this. What we did though was certainly not for nothing, since, as you'll see in a moment, it is going to help us solve this problem. First, let's fully expand the equation that we have. Alright, let's keep this one. Remember that we want to compute the derivative of E with respect to k. So, we'll start with an example, say, the gradient of k21. Now, it would be very tempting to use the chain rule and expand it like this, except that we can't, because these terms are derivatives of matrices with respect to other matrices, and we haven't defined what this means, so it doesn't make sense to write this down. Let's undo this. Instead, we are going to use our helper to solve this problem. Look at the forward propagation equations on the top right and look for k21. It appears only in the second equation, and since the derivative of a sum is the sum of the derivatives, as far as k21 is concerned, y2 only boils down to this. And this is the very same equation that we have in the upper left section of the screen. And so we can immediately write that the derivative of E with respect to k21 is equal to x1 correlated with the derivative of E with respect to y2. And of course, there is nothing special about k21. This can be generalized for any kij. 1 piece out of 3. The next step is the bias gradient. We will proceed in the exact same way, but this one should be easier. And since you know the steps, I will fast forward a bit. This is the actual equation, but let's work on a simplified version. These equations are an equivalent representation of the matrix form. So, we are given the derivative of E with respect to the output, and we need to calculate the derivative of E with respect to the bias. Starting with B11, we expand the chain rule. These are the terms we are looking for. We notice that B11 only appears in the first equation, and therefore, the first derivative is 1 and the others cancel out. Doing the same thing for all the other variables, we can clearly see that the bias gradient is equal to the output gradient. This is what we found, but again, it's the simplified version of the problem. The actual equation is this. The goal is to find the derivative of E with respect to B. So, let's start with an example and compute the derivative of E with respect to B1. Looking at the equations in the upper right corner of the screen, we see that B1 only appears in Y1. Using the helper that we have, we can say that the derivative of E with respect to B1 is equal to the derivative of E with respect to Y1. And this goes for every Bi. 2 pieces out of 3. We can now update the parameters using gradient descent. What's left is the input gradient in order to give it to the previous layer. This one is quite surprising, you'll see. Here we go again. We have the forward propagation equation. We will work on a simplified version, which translates to that set of equations. We are given the derivative of E with respect to the output, and we need to calculate the derivative of E with respect to the input. As you can see, we have to compute 3 by 3, that is 9 derivatives. We can start with the derivative of E with respect to x11. Using the chain rule, we expand that derivative. We are looking for the derivatives of y with respect to x11. x11, in turn, appears in the first equation. Therefore, doing this for all the other x values, you get something unexpected. It seems that each derivative has a different number of terms added in it. And if you remember how we started that video, you might already see where this is going. The result must be some kind of operation between the output gradient and the kernel. Do you see it? This is indeed the pattern that we observe when we make a full cross-correlation. But if you carry out the calculation right now, you'll see something wrong. It is indeed a full cross-correlation, except that the kernel has been rotated by 180 degrees. You can convince yourself this is correct by looking at the animation right now. So, we have figured out that the input gradient is equal to the output gradient fully cross-correlated with the 180 degrees rotated kernel. Wait a second, isn't that the very definition of what the convolution is? Yes, it is. So the final result is that the input gradient is equal to the output gradient fully convolved with the kernel. In my opinion, that is a really compact and beautiful formula. Don't get happy too soon though, this is the simplified version. Let's carry out the calculation for the actual forward equation. Remember that we need to compute the derivative of E with respect to x. We will start with x1 as an example. You can see that x1 appears in every equation. And although we can't write the chain rule, the idea of the chain rule still holds. We need to add up the contribution of each y variable. Using the helper, we can extract the contribution of y1 up until the contribution of yd. This is true not only for x1, but for every xj. And since we're good people here, we will compact this inside a sum. Don't hesitate to take a moment to verify this is all clear to you. After all, if we're doing this from scratch, it is to understand every step of the process. So, we finally have the 3 equations that we needed to complete the backward propagation of the convolutional layer. Let us code the backward method. First, we start by initializing empty arrays for the kernel gradient and the input gradient. Next, we compute the derivative of E with respect to kij inside 2 nested for loops that go through the indices I and j. See how we literally translated the mathematical formula into code. Next, we compute the input gradient. Although this might seem weird to put this line here, if you think about it, it's exactly the same thing as computing this inside 2 separate for loops. Notice how this time we used the convolve method and specified the mode to be full instead of valid. About the bias gradient, we don't have to calculate it since it is equal to the output gradient, which is given as a parameter to the backward method. So finally, the last step is to update the kernels and biases using gradient descent and return the input gradient. Look at that, merely 35 lines of code for the convolutional layer. I mean, this is the core element of computer vision algorithms that are using deep learning today. Talking about computer vision, I would like to show you the capabilities of this layer in practice. As I was saying at the beginning of the video, we could stop here. But if we want to use the layer in practice, we need to implement a few more things. The end goal is to solve the MNIST dataset. In case you don't know what MNIST is, it is a dataset of handwritten digits from 0 to 9. Here's a sample from the dataset. Each one of these images is 28 by 28 pixels in grayscale. The goal is to make a neural network capable of telling what number is written on a given image. Now, the truth is, our code isn't super optimized, and currently we are bounded to the computational power of the CPU. And for these reasons, it might take a while to train a neural network on the whole dataset, which contains 60,000 images. Therefore, for this example, I decided to limit the classification to only 2 digits. You'll see later in the code that I chose 0 and 1, but nothing prevents you from changing that. Now that you know where we are going, let me tell you why we need each of the following things. The reshape layer is needed because the output of the convolutional layer is a 3D block, and typically, at the end of a network, we use dense layers, which take in a column vector as input. Therefore, we need a mechanism that reshapes data, hence the reshape layer. The binary cross entropy loss is because we decided to make a classification on 2 digits. In other words, a binary classification, and this loss is pretty good for that task. Lastly, the sigmoid activation. If you don't know it yet, the binary cross entropy uses the logarithm function, and the logarithm function cannot take negative inputs. Therefore, we are going to implement the sigmoid activation since its output is bounded in between 0 and 1. Let's start with the reshape layer. The reshape layer, like all the other layers, inherits from the base layer class. Its constructor takes in the shape of the input and the shape of the output. The forward method reshapes the input to the output shape, and the backward method reshapes the output to the input shape. And that's it. Now, the binary cross entropy. Basically, you are given a vector containing the desired output of the neural network. Since we are making a binary classification, and this is what the binary cross entropy is for, each of the values inside that vector must be either a 0 or a 1. Then, you are given the actual output of the neural network. The binary cross entropy loss is defined as the following. The goal is to compute the derivative of E with respect to the output, which is what we give to the backward method of the last layer of the neural network. As an example, let's start with y1. We replace the actual value of E. We can expand the sum to see what's going on, and notice that y1 only appears in the first term. Therefore, the derivative of log of y is 1 over y. Regarding log of 1 minus y, you simply apply the chain rule, and you get this. Of course, there is nothing special about y1, and this is true for every yi. We have these two formulas. We can implement them inside 2 separate functions. Note that yTrue and yPred are not scalars, but vectors. We are using NumPy's capability to perform operations on arrays. So, when we write yTrue times log of yPred, NumPy is going to multiply every value of vector yTrue with the log of adjacent values in yPred. So it's basically doing what we want. The last step before we can implement a convolutional neural network is the sigmoid activation. The sigmoid activation is defined as 1 over 1 plus the exponential of minus x. As I already said, it is bounded in between 0 and 1. Its derivative can be expressed in terms of the function sigmoid itself, and it looks like this. We implement both of these functions by creating a new class that inherits from the base activation class that we created in the previous video. Alright, at last, we are ready to implement a convolutional neural network from scratch that can classify the MNIST images. Without waiting any longer, here is the final piece of code. We start by loading the MNIST dataset using a utility from the Keras library. So the next step is to limit the data to only 2 classes. The preprocessed data method does exactly that. First, we get the indices of images representing a 1 or a 0. Then, we stack these arrays of numbers together and shuffle them. Then we extract only the images at these indices. Regarding the images, we reshape each image, which is 28 by 28 pixels, to a 3D block of 1 by 28 by 28 pixels. That is because the convolutional layer, as we created it, takes in a 3D block of data with the depth as the first dimension. Since the images contain numbers in between 0 and 255, we normalize the input by dividing each value by 255. Regarding the output vector, we use another utility from Keras that will create a one-hot encoded vector from a number. Essentially, the 0 will become a vector containing a 1 followed by a 0, and the 1 will become a vector containing a 0 followed by a 1. We reshape these vectors to be column vectors, since this is what the dense layer takes in as input. Then, we create the actual neural network. The first layer is a convolutional layer containing 5 kernels, each containing matrices of size 3 by 3. We activate the result using a sigmoid, then reshape the output into a column vector. We pass that column vector into a dense layer that maps it to 100 units, activate it again, then map the 100 units to only 2 units. There is a final activation, as always, and that will produce the output of the network. The rest of the code contains the training loop, which is exactly the same code that we had in the previous video, except that this time we are using the Binary Cross Entropy Loss. If you run this code, you will see a decreasing error and a final prediction on the test set, and the results are pretty good. At this point, the best thing to do would be to play around with the code, execute it, and see how it behaves for yourself. That's it for this video. Feel free to leave a comment if you have any question. Also, any feedback is greatly appreciated, whatever its nature, I promise. These truly encourage me to keep going and make these videos better. So really, don't hesitate. See you soon.